Okay, uncertainty part 3. Now we have a pretty good understanding of accuracy issues, of mapped features and their attributes. So let's talk about how errors get on maps. Sources of error. There are a lot of them, and I'm just going to run through a kind of a list to just maybe overwhelm you with how many ways we can introduce error into our data. There's measurement errors, obviously. We have errors that can come from precision, misjudgments, inappropriately applying scale, generalizations that we make, human error, using the instrument incorrectly when we're collecting data, selecting the wrong coordinate system to make measurements in, incorrectly locating sample locations. We can have data model representation errors, so choosing vector as our data format when it really should be raster, interpolating values incorrectly. Anyway, that's pretty obvious. Propagated errors coming in from secondary data. We're going to talk about cascading effects and propagation in just a second. Formatting issues, and this is a big problem. This is where we can get into that kind of slow deterioration. We can reproject data incorrectly. We can do coordinate transformations incorrectly. We could be using the wrong datum. Conversions between raster and vector data. Getting into that deterioration. You can have cat sleeping on your keyboard errors, right? I know, so cute. Factual errors. Oh, you know what? I think I even have more. Yeah, numerical errors. So ArcGIS will, when you're dealing with integer attribute fields, will sometimes truncate. And I'm not saying they do it like they just willy-nilly decide behind the scenes, but there are some formats that will truncate your values, and then there are other situations where the values will be rounded. And it's really hard to know the difference, so you do need to be aware that sometimes when you set up fields, there are certain ways you can set them up that your values will be truncated versus rounded. Physiological errors, like your inability to just get the cursor at the right location or to trace along a path correctly when you're digitizing. You can have a hand cramp. There's just so many ways that can lead to different kinds of errors. Topology errors are things that can affect networking and connections when you're digitizing, and I'm going to just go over that in 1 second here. But first, let's talk about factual errors. These are some fun examples. So you just got done working with this bed map data from Antarctica, and you might remember that the peak of Mount Vinson was measured on the DEM at 4,408 meters. The generally accepted survey elevation is 4,890 meters, quite a bit higher. And that difference is at least partially explained by the resolution of the data set, which we talked about in the last lab. And then BedMap 2 came out. This is an updated DEM for Antarctica. It was released in 2012, and I started to update the lab with this new data and found a glaring mistake. The high value for the DEM was only 3,972 meters. This means that the peak of Mount Vinson had dropped by 400 meters from BedMap 1 and was now over 900 meters lower than the surveyed height. So I wrote to the lead author of the BedMap 2 paper. I felt a little bit awkward doing that. I mean, I'm a lowly GIS instructor. But I asked for an explanation, like, was Antarctica actually subsiding? I read all their metadata and I just could not figure out what was going on. How could they miss something so obvious? There had to be an explanation. And he wrote back to me almost immediately, which I was absolutely shocked by. And he said, yeah, it seems like the mountains here are smoother than they should be, and if the proper data had actually been used. He thinks that some kind of smoothing algorithm had actually rounded all these peaks, and nobody had caught it. Isn't that awesome? So it just goes to show that even in these massive data releases that are checked and cross-checked and collaborative, something that glaring could sneak through. It just goes to show that, there are some big errors out there, and these are easy ones to catch. It's the little sneaky ones that can really systematically kind of drag you down, I think. So anyway, they did release a new DEM that covers a very small spatial extent of the region around Mount Vinson, and that one has a peak cell value that's very close to the surveyed value of 4,890. So anyway, for what that's worth. This is another really fun example of a factual error. In 2010, October of 2010, I don't know, you guys maybe heard about this, Nicaragua invaded Costa Rica, acted like a big jerk, and then blamed Google Maps. And that's exactly what they did. Google Map had the the border between the two countries wrong. And the river comes down here, and Nicaragua used it as an excuse to go in and invade, and started dredging the river to actually change it so that they could claim this territory. They wanted this land. Bing Maps had it right, and yeah, I don't know that we can actually blame Google Map. I think that you could probably blame Nicaragua for being a big jerk and using something like Google Maps to base their military decisions on, but yeah. Factual errors are user error, equipment errors, misclassifications, wrong names, incorrect symbology. They're like typos, and sometimes they can be really dangerous typos. Yeah, okay, so topological errors. Topology is, it describes rules that describe how geographic elements interact with each other. And so we're really talking about things like state boundaries need to be coincident, right? I mean, Iowa and Minnesota, that boundary needs to be in the same place, whether it's the edge of Iowa or the edge of Minnesota. For network things, it can have to do with two roads that intersect on a map and they look like they overlap. You need to be able to know if you can take a right turn from one road to the other, or is it a freeway overpass in a dirt road. So those are the kinds of things that topology describes. When we're digitizing, they have funny names like dangles, switchbacks, knots, loops, overshoots, undershoots, slivers. So these are those kinds of things I'm talking about. And in geodatabases, you can set up topology rules to catch things like this. But yeah, you should just in the very least know that they are there. So intersections and overlap, this is kind of what I'm talking about. If you've got a really complicated set of lines, topology needs to be able to state which are over, which are under, which connect, which lead to one another, so that networks can flow appropriately. All right, so error propagation. Propagation is a term that means one error is leading to another. Cascading effects means that errors are allowed to propagate unchecked from one output to the next, and that can end up deteriorating your data and leading to really large margins of error that might not even be noticed or accounted for in any way. You can manage these kinds of problems with sensitivity analysis. When you add multiple sources of data together, which is what GIS is so good at, the varying magnitudes and types of error are going to be added to each other and can just compound the problem. Sensitivity analysis is it's the study of how variation or uncertainty in the output of a model can be attributed to different sources of variation in the inputs. So we can measure change in the output when input variables are manipulated. That's what it measures, sensitivity analysis, and hopefully you have some experience with that. I didn't do a very good job of explaining that just now. Sorry. Sensitivity analysis is better than this management of error, for sure. So dealing with error, visual inspection is a great way to deal with error, to be totally honest with you. Sometimes you just have to look at it and see what you've got. You can control the quality of your measurements up front. You can develop standards. You can follow standards. You can try and minimize human error. I love the word prevent. You really cannot prevent human error. But you can certainly try and minimize it or account for it. You can check out the data quality reports. Data quality reports include how data was collected, from what sources, how it was pre-processed and geocoded, how it was entered into the data set, how it was classified. Those types of things are really important, and a lot of government data and professional data does have a corresponding data quality report. And I would love to tell you that you should always be creating data quality reports for all the data you create, but I would be a total hypocrite because I don't. But it is a lot easier to make it while you're creating your data than to have to make up the data quality report after the fact. If you're doing research, you know your data is going to be published, you'd be well served to deal with some of these things right up front, because trying to do it later can be a real hassle. Also with data models, you want to select the correct data model based on your experience with what's going on or the model appropriateness, and try to reduce errors during conversion from one data model to the other or transforming between coordinate systems, for sure. All right, identifying and measuring errors in GIS. Surveying, when we're dealing with DEMs in particular, we just walked through this example. So, like I said, RMSE compares predicted against observed locations and values at locations to determine the distance both in the horizontal or the vertical positions. So again, what you're going to do is, I forgot to say that there are statistical methods that can be employed as well as visual inspection, which I mentioned in the last slide. But estimating the degree of error helps in controlling and correcting errors. And one way we can do that is with RMSE. We are going to compare the differences between known and predicted values. We're going to square them. Here, I'll just show you an example. Here's an example where we have a DEM, and underneath we have a map where we went out and surveyed specific sites and have known high-quality surveyed elevations. Okay, so let me bring in my Excel worksheet and I'll show you what I did to set up this example. I went in and put in all my surveyed elevations for my points, and then I ran an extract value point tool, which will pull the elevations from the DEM at the survey point locations, and then I put those interpolated values in this Excel spreadsheet. So I've got my survey point locations, I extracted the cell values at those same locations, then I can difference them, just subtract them, and I can square them to get rid of the negatives and get absolute values. And then I summed them. Then I divided by the number of observations, which was 10. I got my count. And then took the square root. And that gives me a vertical accuracy for this data set of 4 meters. So that kind of makes sense. It's a really straightforward Excel exercise, and I would be certainly happy to set up some sort of exercise if you guys want to walk through this yourself. So this made-up scenario here has a 4 meter vertical accuracy. So any elevation I pull has a margin of error of 4 meters, which means I shouldn't be reporting elevations to the nearest millimeter also, right? Okay, so metadata, this is really important stuff, and if you haven't worked with metadata, if you haven't created metadata, you can't do it in your standard ArcGIS connection to ArcCatalog. That's kind of a limited usability, limited utility ArcCatalog. You have to go into the standalone ArcCatalog. But then you can go into the description of any given data set and you can edit it. You can add a thumbnail of the data, you can write a summary, describe what its uses are, limitations on the uses of the data, data credits, and you can start to provide a data quality report for the data that you create. So data about data. What, who, where, when, why, how, the scale, projection, transformation information, the lineage, different field names if they've been abbreviated and might not be clear, any known instrumentation errors. This is the kind of thing that can help you evaluate the appropriateness of your data. And whether you have access to metadata or access to a data quality report, it's a good idea to just sit down and ask yourself what you know about any data that you're going to be using to do some analysis. And this is just a standard list of things that you should question. What scale is this data meant to be used at, right? What's the precision that measurements were taken with, and how can you propagate that forward? How well does the data correspond to the real world? What's the lineage of the data? Where did it come from? What's been done to it since it was created? How current is it? What kind of documentation is available? And then have any basic standards been applied? All right. So that's pretty much it. I love this quote of Donald Rumsfeld's, especially about data quality, because everything that we could possibly try to quantify in GIS, it's not going to get you all the way there. There's also going to be all the stuff you don't know that you don't know, right? I mean, this is so perfectly stated. You got a lot of flack for it, but it's very true. So the moral of the story is be aware of data uncertainty, period. I want you to be a GIS superhero, not a GIS super dud. You're going to have to account for uncertainty in your final project, so keep data quality in mind for the rest of the semester as we work through the rest of the labs. And that's it. It can be a super interesting thing, and when you are doing your own analysis and you discover some errors or uncertainty, it can be really satisfying, strangely enough. So that's it. Thanks for your time, and if you have questions, let me know. Thanks.